Today we're going to talk about magnetic isopotential lines. Now, these are the lines that are generated by software written by Michael Snyder. Michael Snyder works in collaboration with Timm Vanderelli on trying to figure out how the ferrocell works. And so his software generates the isopotential lines around a magnet. So first what I want to do is I want to recap what is an isopotential line. Now, iso means equal. Okay, so really these are equal potential lines. Now, equal potential lines are normally associated with electric dipole. So in the equal potential lines, the electric potential is measured along the line, and electric potential is voltage. And so equal potential line in this case is equal voltage lines. And this is going to be important because what I'm going to show you in a minute is an experiment I did to reproduce the isopotential lines in and around a spherical magnet. Okay, so the equal potential lines are always perpendicular to the electric field. So if these black lines are the electric field, these red dashed lines are the equal potential lines. And as you will see, or as you can see, these equal potential lines, which are the dashed lines in this image, correspond to the equal potential lines or the isopotential lines generated by Michael Snyder's software. So they are one in the same. And actually you can't see it in this image, but when you look at this image, I zoomed in a little bit and overlaid the electric potential lines with the isopotential lines from Michael's software. You can see, and actually I'm going to zoom in. Oh, let me try to zoom in a little bit here. So you can see the software, Michael's software, also generates the orthogonal lines which correspond to the electric field. So these little red and blue dashes here actually correspond to the let me just zoom out a little bit more here. Okay, so these lines here, hopefully you can see them in the video, line up with these lines. And so you can see this potential line exactly matches one of the potential lines from the magnetic potential. Okay, so really the equipotential lines of an electric field are the magnetic field. Okay, so the magnetic field is always there, I believe, at least the equipotential field, the equipotential is always there. So let's move on. So here's my experimental setup. Okay, the experimental setup, what I'm going to be doing is I'm going to be measuring the equal potential lines in and around this spherical magnet. Okay, so we're going to start with the Hall sensor. Now, I got this device from Carrie from the Good Vibrations channel. I think I've mentioned him a couple times already in my videos. And so he uses this device. He built this device. Basically what he did was he gutted a phone, an old portable phone, just and he put a circuit in there. So this is just the housing for his circuit, and then coming out of the phone is the sensor, and this little thing at the end here is actually the Hall sensor. So what is a Hall sensor? Okay, and he gets them from K&J Magnetics. The ones that he buys, he gets from K&J Magnetics. So a Hall effect sensor is a device that is used to measure the magnitude of a magnetic field. Its output voltage is directly proportional to the magnetic field strength through it. So the key here is voltage, because voltage is potential, and the potential is proportional to the magnetic field strength. So this is what we're going to be measuring in this experiment. So I'm going to play a little video for you to shows how this device is used to to generate a voltage, and it's basically called the Hall effect.
Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879.
So that's basically what we're going to be doing. We're going to be using this Hall sensor, measuring the voltage. Okay, so another part of the next part of this this experiment is the voltmeter. So Carrie also sent me this voltmeter, and I'm pretty sure it's a brand new one because it still had the little plastic thing on it when he sent it. So thank you very much for that. That's very generous. He sent me this, and he sent me this. So that's, you know, part of my setup here. I'm also using a pole finder, which I bought fairly recently, and I use that, of course, to detect which pole I'm looking at. South is green and north is red. So right now I'm pointing to the south pole of the magnet because this is green. Okay, so what I want to show you here is, okay, so the next part of the experiment is the sphere magnet. Okay, the sphere magnet, I drew a black line. I don't know if you can see this in the video, but I drew a little black line, which is the dielectric inertial plane, the block wall, whatever you want to call it, the halfway point between north and south. I also put a little ball bearing. I attached a little ball bearing to the magnet. I just put it on the magnet and it forced itself into this position. And I do that, so this would be the North Pole up here. And I do that on purpose so that in my video I can quickly and easily see which is the North Pole and which is the South Pole. The South Pole doesn't have a ball bearing and the North Pole has a ball bearing. So that's why I put that little ball bearing there, is just for me to easily, quickly know that that is the North Pole. Okay, so in this setup, north is up, south is down. The little ball bearing is on the north. Okay, and I'm enhancing the dielectric inertial plane right here, the halfway point, just so you can easily see it. And the voltmeter is reading 1.41. I also use the magnetic viewing film just to verify that I did in fact draw my black line on my magnet in the right spot, because I can see in the magnetic viewing film, I can see the inertial plane showing up right there. So that's why that is there. So the first experiment is just a quick one to show how this Hall sensor works. Okay, so when the Hall sensor is touching the North Pole in this orientation, okay, I'm getting a reading of 1.41. North is up, south is down. Okay, now when I put the Hall sensor on the other side of the magnet, so now it's touching the South Pole, I am also getting a reading of 1.41. Now, if you want to find out more about this, you should check out the video, a couple of videos made by the Good Vibrations channel by Carrie in his The Good Vibration channel, which I actually linked the video I want you to watch in the description. So he does a very more in detailed description of this and explains it in terms of his theory. Okay, so I'm just going to quickly show you what happens. Now when I turn the magnet and north is down and south is up, okay, you can see the red light is on here, so the North Pole is now down. You can see that when I touch the meter, when I touch the Hall sensor to the magnet, I get a reading of 144. So it reads differently when you flip the magnet. And according to Carrie, the Good Vibrations guy, this is due to the imperfection of the manufacturing of the Hall sensor and really has nothing to do with the magnet whatsoever. So now you can see what I'm going to show you here is when I move the sensor to the opposite side, I still get a reading of 144. In fact, it's minus 1.44. Okay, now it's in the negative. So when I flip the magnet, now I'm getting a negative reading. Now I'm not going to explain Carrie's theory here. I'll let him do that. But I just wanted to show you that there is a difference between when north is up and north is down. And so I have to be careful how I do my experiment. This is the orientation I'm going to use. With the North Pole, you can see the ball bearing is pointing down. Okay, so here's a little video I made where I show what I'm going to do to generate the isopotential lines. Okay, so I'm just going to play it a little bit. So basically what I do is I come in toward the magnet slowly, and what I'm trying to do is I'm trying to stop at minus 0.06. So you can see as I get closer, the numbers get bigger. So I'm always approaching the magnet from the same direction because of the bias in the system, because of hysteresis. It's best to always approach the magnet from one direction. And so, and then I stop when I get to minus 0.06. Okay, so there's where I stopped. You can see it reads minus 0.06. This is where I stop. And so what I do is I just take my little pencil right here and I draw a little dot underneath where the sensor was. So this is a really crude experiment. It's not, you know, not rocket science, but it really is, you know, not too bad considering the calibration error of the Hall sensor. It's a cheap Hall sensor. I don't know if it's cheap, but it's mass manufactured device, and so it's not perfect. And so I have to be really careful about how I do this experiment. So then what I do is I go around the magnet. Okay, so when I always have to approach the magnet from the same direction. So because this is a spherical magnet, basically what I'm trying to do is I'm trying to be orthogonal to a radial line that goes through the center of the magnet. And I'm just eyeballing it for this particular purpose. But basically what I want to do is I want the Hall sensor to be normal to the surface of the magnet. And that's why I keep changing the direction. You can see, you know, on the right I have to go that way, on the left I have to go that way. And then as I go, you know, as I go around the magnet, I'm always trying to stay relatively normal to the surface. So here you can see as I get close to the dielectric inertial plane, to the middle part, I have to get in closer to the magnet in order to get a reading of minus 0.06. Okay, and so the reason, now I'm going to just go one more here. So now I'm actually touching the dielectric inertial plane and I'm getting a reading of minus 1.43. So the reading really jumped up, and here's why. The region, so there is zero potential at the dielectric inertial plane, but if you go a little bit above, now I'm going to show you sort of closer. So now when the Hall sensor is a little bit above the dielectric inertial plane, I get a reading of minus 1.43. But when I go a little bit below the dielectric inertial line, I get a reading of positive, the negative sign went away, positive 1.39. Okay, so it's negative on this side of the line and positive on this side of the line, and 0 is somewhere in between. So 0 is, and 0.06 in particular, is very hard to find. So I have, because I'm just hand holding this, I don't have it on any kind of motorized jig or anything. It was very difficult to find that particular spot. Okay, so, but when I move away from the magnet a little bit, and I'm still very close to this dielectric plane, but I'm above a little bit, and if I move away, I very quickly get to the minus 0.06 reading. And so I marked that spot. Okay, and then there's another one, minus 0.06. So whenever I find a minus 0.06, I put a little dot underneath the Hall sensor. Okay, so there's a bunch of spots. So on the other side, I have to turn it around because that's the way the Hall sensor works. If I turn the Hall sensor around the other way, I'm going to get a different reading. The 0.06 minus 0.06 is going to be in a different location. So it's going to be in the wrong spot. So there, I'm coming in to I'm getting close to the dielectric inertial plane. There's a reading of minus 0.06. And then on that side, I was actually able to find, almost touching the magnet, I was able to find a 0.06 minus, well, this is actually 0.06. But basically, I was able to get very close to the value that I was looking for. And so once I was done marking all my points, this is what I ended up with. So this is one isopotential line, one equal potential line of voltage readings. Okay, each voltage reading was minus 0.06, minus 0.06, which was very difficult to read once I got close to the magnet. But basically, I got a pretty nice isopotential line, which when I registered to the isopotential image that I generated, so I generated this isopotential image using Michael Snyder's software, you can see that my dots land on the isopotential line that he generates. So from my experimental points fit very nicely to his calculation. So, this is really nice. This proves, okay, it proves that there are measurable isopotential lines around a magnet. Not that that was necessarily in doubt, but I have had some arguments with people about it. And so I think it's important to know that these isopotential lines do exist in and around a magnet, and I just measured it. So now the trick is to see if these isopotential lines, so the real argument is whether the isopotential lines correspond to what we see under the ferrocell, or the other way around, do the lines in the ferrocell correspond to isopotential lines? And so here is the sphere that I used, okay, to generate the lines. Now, I'm just going to show you a quick demo of Michael's software. Basically, what you do is you input an image with a red and a blue, red and blue colors. Red represents north and blue represents south, and then you run his software. So it's just a command line. It's not really fancy, just a command line. It's called pic2mag, and then you type in the name of the file that you created, .png. Okay, then it goes through a bunch of calculations, right? It is doing some number crunching right now, and then now it's processing, and it's writing all the files, and then it's done. So, and basically this is what he generates, this image here. So I generated this image using his software and then blended it with my experimental points to get the alignment. Okay, so here's some images from the paper. Okay, this paper that I was just, the investigation of light patterns in a ferro lens subject to a magnetic field. So basically it's the ferro lens, aka the ferro cell. So here are a few images from that paper. And so it really does look like, looks a little bit like the lines in the ferro cell match up with the lines in the isopotential lines from the software. Okay, so this one is actually really interesting because you see this black region here, which is a little bit distorted. It's got kind of a chiral symmetry, matches this black region in here, which has a very similar chiral symmetry. Okay, so we can look at this a little closer. What I did was I put the images on top of each other. Okay, I'm going to just format the picture here, and I'm going to show you that you can blend these two images and get a better idea of how the isopotential lines line up. And here's something interesting I found with this one. Now I don't know if it means anything, but when I registered these two images, I discovered that, so this is the configuration he used in his software. Okay, and it looks like these black regions here, right, are matching up with these sort of red X's, these little red X's, which they exactly match up, which makes me very suspicious that they're related somehow. So I don't know what that means. It's just something to look at. It's kind of cool. I don't know, like these are where the isopotential lines are crossing each other, and maybe when they cross each other they cancel out, and you get this, you know, the light doesn't go to your eyes. So so that's that image. The next one is also interesting. I can do the format the picture, do transparency on that one, and you see that this shape here does match up very nicely with this shape here. And the isopotential lines, see, this is the thing with the ferrocell, the isopotential lines are not exactly, they're approximate, they're more distorted, they're more they look more like an interference, they look like more like the interference than they do the actual isopotential lines. But the dark regions do match. Okay, this region where the isopotential lines are, you know, very dark, match with this dark region. So that's kind of cool. And then let's have a look at some other ones. Okay, Michael recreated this configuration in the ferrocell, and so this is actually software from my software that I developed from work, where I can take two images side by side and I can alpha blend them. The one on the left is alpha blended and the one on the right stays the same. So it allows me to investigate the blending and look at the original image at the same time. Okay, and here's something I noticed, and I don't know if you can see it in the video, but it almost looks like the potential lines down here that are straight seem to match these lines down here that are straight, and these lines like in between, they seem to match really nicely. Just in the middle here, you see the in the ferrocell image with ferrocell on the left, simulated on the right, they seem to be crossing each other. And they also seem to be matching a little bit there's a bit of a moire pattern in here just because I shrunk the image down, a little bit of an interference pattern. And so it makes me wonder if there isn't some interference going on. And you think there should be interference going on if the ferrocell is in fact a diffraction grating, because that's what diffraction gratings create, interference patterns. So this is just getting me thinking a little bit about interference. Here's another one that I registered, and you can kind of see a similar thing where the potential lines, so this one shows the potential lines really nicely. They're very similar. These lines are straight here, these lines are straight here, these lines are coming in from the side, these lines are coming in from the side, but in the middle here, where you have a lot of sort of a moire effect in this image, you tend to get some crossing. The crossings are happening. So really in the ferro lens, in the ferrocell, the lines are highly dependent on where the lights are placed. And so it seems like the ferro lens is trying to show isopotential lines, but then there's some interference going on. And I think I got one more here. So here's another one, another configuration. He's got 3 south poles here, and he built the same configuration and visualize it under the ferrocell. And you can see, so this is really interesting. This part in here tends to match this part in here where the iso lines are really far apart. When the iso lines are really far apart, in the ferrocell, you seem to see kind of a blurring. But really, I mean, the isopotential lines are circular around this magnet, but they're crossing around in reality in the ferrocell. So the ferrocell isn't showing exactly the isopotential lines. Okay, so let's get back to my PowerPoint. So I just recently received a bunch of images from Michael Snyder. He used his software to generate the rest of the electron orbitals. So in my previous video where I talked about the electron orbitals, here you see this is the first set. This is the first iteration, I guess you could call it. And here are the isopotential lines that Michael generated with his software. And this is the second iteration. This is the second iteration where you've got the outer bigger magnets and the inner smaller magnets, and you've got a similar configuration for the electron potentials, and you can see that the images are very similar. And then he also did the third iteration where, you know, the images I got were a little cut off, but basically I think, you know, you can see when you zoom in. So here's another, let me just format this picture. Here's another alpha blending that I'm doing, right, where I zoomed into the middle of the third iteration, and you can see that these shapes, the shapes that we're seeing here, are really closely correlated to the shapes that the software generates. And so especially if you look at the in-betweens, if you look in between, you see that there's, you know, quite a similar thing going on here between the electron orbital probability distributions generated by whatever software they use to generate that, and then with Michael's software. So obviously these two, the software used to generate the equations, I'm going to say, used to generate electron orbitals is this, or must be the same equations that Michael is using in his software. So that's about it. I'm going to leave it at that. And there's a lot going on. There's a lot more to do, but I think one piece at a time. Obviously, the ferrocell still needs to be understood. I really do think, though, that it is, you know, the isopotential lines that we're seeing, or the lines that we're seeing in the ferrocell, are related to the isopotential lines. And I think we need to look at that a little closer. So I hope you guys are hanging in there. I've been a little bit, you know, having a little more time, obviously, because we're isolated. It's coronavirus time, and you know, we're doing our social distancing. But trying to connect myself with people in this manner. So I hope you guys are hanging in there, and I will talk to you soon.